to maybe what I need to talk about. So I want to do that because some of the homework that's come in, there's been a problem. And I'm looking at the 2-3 homework, and you don't need it. If you want to turn it in, that's fine, but you do pay attention. The one problem says, write the equation of the cubic polynomial. So it stipulates cubic, and it says it has zeros, 1 with multiplicity 2. Now that means that 1 happens twice. So in other words, the factor x minus 1 is squared. And then another one is -3. It just says it has another 0, -3. So that would be x plus 3. Write the equation of the cubic polynomial. Now, will this be cubic? Yep, perfect. However, it must contain the point 4, 7. So there are infinitely many cubic polynomials that bounce off the x-axis at 1 and pass through -3. We want the particular one that contains that point, so we need to find out what leading coefficient will control that, right? Okay, so 7 is the y, x is 4. So 7 equals n times 9 times 7. So does n equal 1, 9? No. So my equation would look like this. Now, I didn't stipulate that you had to multiply it out. I didn't stipulate you didn't. So some of you probably did. FOIL all this out, distribute the 1, 9. In this, I'm just leaving it like this. All right, so multiplicity is how many times the root happens, which tells you what your exponent is on the factor. Tess?
So if it asks us first equation, should we keep that like that?
This is an equation. So sometimes I will say, like on a quiz or test, I will say multiply out. And you have to multiply it out. If I don't say that, you don't have to. Ma'am?
Can you please do B, because I don't understand the 0 at -1 plus pi.
Okay, not right now. Now I'm going to talk about number 5, which is, I have this graph, and it crosses the x, oh wait, true or false? It crosses the x-axis between 1 and 2. So, I don't know what that thing looks like, but I am going to try to figure out if it crosses the x-axis between 1 and 2. So, I'm going to go ahead and plug 1 in. What do I get when I plug in 1?
-2.
I get -2. Now keep in mind that means when we say f of 1 equals -2, that means the point 1 comma -2 is on the graph. That's an ordered pair. All right, what do I get when I plug in 2? 8 minus 4 minus 2. I think I get positive 2, don't I? So what point is that? 2, 2. Now, this is a cubic polynomial. It is a continuous thing, right? These 2 dots have to be connected. Does it cross between 1 and 2? It absolutely does, because the y's have a sign change. So don't I have to go from one side of the x-axis to the other? It's an absolute guarantee that there's a 0 in there. Now where is it? I don't know. We haven't figured that out. But I know it's in there because these dots have to be connected. Right? Perfect. All right, that's all I'm going to do right now. Remember, we have office hours for specific questions that you might have. If I have time, I'll come back, but we've got to keep plowing ahead. We got a lot of math to do in this chapter. All right, what was the very last thing? Who was paying attention? What was the very last thing we talked about? Upper and lower bounds. And what did we say about upper and lower bounds? When you did your synthetic division, the quotient line was all positive. That meant you had upper bound. And if the quotient line alternated, that means you have a lower bound. So the question A3A says, is 5 an upper bound? Well, let's divide and see what happens. So 2 minus 7 minus 8, 14 and 8. One thing we didn't talk about, remember when you do synthetic division, if a power is missing in the problem, like if there had been no cubed in there, you would have to put a 0. You remember that rule? So I'm always real careful when I have these big long problems that everything is there. All right, so let's see, that's 10, 3, 7. Oh, it looks promising here. I don't know, it's gonna be positive, right? Is it an upper bound? Yep, because the whole quotient row is positive. Is -2 a lower bound? Same problem. Sure I'm doing this right. Is -2 a lower bound? Looks like it, if I didn't make too many careless mistakes.
Wait, yeah, where'd you get -2?
This -2? Read the question. Question B.
Oh, sorry.
No, A is done. We were checking 5. 5's a yes. We're done. So then we moved on to see if this was a lower bound, and it is. Now, if we were in the middle of this problem and we were trying to find all the zeros and graph, what is the fact that 5 is an upper bound and -2 is a lower bound? What does that tell me about all of the zeros of the problem? They're in between. So remember when you build your possible rational roots and you would do factors of 8 over factors of 2? Some of those you wouldn't even consider because you know they can't be bigger than 5 or less than -2, right? So this doesn't give you the answers, but it kind of narrows it down a little bit more for you as you're doing your guessing procedure. All right, now we've got this polynomial. This is kind of like the one in the homework. Maybe not. Show that all of the real zeros lie between 0 and 1. So that means when you graph that, every single, there's 5 zeros. Every single real 0 is going to be just in that little tiny space. Isn't that kind of this idea over here? Because didn't you tell me over here that all the zeros were between -2 and 5? So if all of the zeros have to be in here, then shouldn't 1 be an upper bound? Watch your division, we have some missing things. So 10, 0, 0, -3, 1, -6. Sometimes I get a little ahead of myself here. I think that's right. Is 1 an upper bound?
Yes.
Yeah, so that means there are no real roots. If you graph this thing, there are gonna be no x-intercepts bigger than 1. They're all gonna be less than 1. Okay. Now, behind the TV. don't normally do synthetic division with 0 because what factor, if you were checking to see if this is a factor, and that's normally when you do the division, what factor would that represent? Just x, a plain x. And normally we don't need to divide that out because if plain x is a factor, aren't you able to just factor out the x? You don't have to do the division. This is the factor x minus 1, so that would require us to do division. But, so normally we don't do zeros out here. Remember, we're not dividing by 0. We're dividing by x. That's what's happening here. You're dividing by x. Now, take a look at these numbers. Remember that 0 is unsigned. It is not negative and it is not positive. So basically we can ignore the zeros that are not part of the alternating. They're just not signed. They don't have a sign. So if we look at the numbers that do have signs, what's happening? They're alternating. So 0 is a lower bound. These are not signed, so they can't be counted as positive or negative. So they're kind of out of the mix. So, have we proven that every real 0 lies between 0 and 1? Yep, we sure did. We sure did. All right, find the remainder of this division by division and by using the remainder theorem. You probably know what the remainder theorem is, but let's do the division first. So if I do the division, out here is going to go a 1, right? X minus 1 is my factor. So I'm going to put 1 out here. And then be careful here, 1, 0 cubed, 0 squared, 0 linear, negative 5. So I'm just dividing, finding the remainder. Now where's the remainder in all this?
Negative here.
Right there's the remainder, right? Now that tells me something. That tells me that x minus 1 is not a factor of this polynomial. Because if it were a factor, the remainder would have come out to be 0, and it didn't. But my job was just to find the remainder, so that's what I did. I got negative 4. Okay, now I want you to consider the thing, the dividend, the thing we divided by. Think of it as a function, x to the 4th minus 5, or x to the 4th minus 5. And instead of doing the division, just plug in the number that you were dividing by. So think of your dividend, your thing you're dividing, think of it as a function, and then plug in the number you were dividing by. What do you get if you plug in 1? You get the remainder. You get the remainder. So if all you care about is the remainder, you can just plug that in, and it will give you the remainder every time. And of course, we talked about the other day, if you plug it in and get 0, then you've got a root, because that number's a remainder, and when it was 0, that meant you had a factor. This can be really helpful if, for example, you were asked some big, huge, hideous problem like, is x plus 1 a factor of 3x to the 99th minus 4x to the 10th plus 5x cubed minus 8, something like that. Nobody wants to divide, because if you divide, it's going to be huge with all the zeros in there. So instead, just evaluate this thing at -1, and then you can tell what you that would be -3 minus 4 minus 5 minus 8. It is not, so no, because the remainder isn't 0. All right. This is called, this plugging in thing is called the factor remainder theorem or the remainder factor theorem because it gives you the remainder, and if the remainder happens to be 0, you have found a factor, a root. Yep. Yep. So when somebody talks about the factor remainder theorem, that's it. Just plug in whatever you would divide by and hope you get 0. All right, find all the zeros of this guy. Here we go. Here we go, starting from scratch. We got nothing. You're not gonna factor it by grouping. So what do? What's going through your head right now?
Rational.
This is the lunch period, is it? Possible rational roots. Possible rational roots. Factors of 6 over 1. We like it when there's a 1 out here. Because if there's not a 1 out there, then your PRRs would include fractions. But we don't have to worry about that. All right, so these are our possible rational roots. Okay, now what?
Synthetic division.
Do synthetic division. What do you want to divide by?
Let's try 1.
By 1?
Try 3.
I don't like
I think
1.
we should do 2.
2? All right, we'll try 2. You know what I was oh, that didn't work out. Let me double check. Did I make a mistake? Somebody said 2, so I did 2.
No, it didn't work.
Yeah, it didn't work. Somebody originally suggested 1. 1's a great number. I use it a lot. But I didn't do 1 because in my head, I plugged in 1 and could see that it wasn't going to be 0. Remember, you can check by plugging as well as by division. So this told me 2 didn't work. How about -2? Will -2 work? Nope, I don't think -2 works either. Unless I messed up.
Yeah, -3.
-3? 3 doesn't work either. Am I wasting my time?
No, but positive.
-3 does. Oh, yeah, there we go, we got it. So what are we doing? Finding all the zeros. So one of our zeros is -3. Would everyone agree with that? Does this take a certain amount of luck and perseverance? Yeah, just gotta keep going till you find one. Okay, now what do? We've got it divided out, we got a remainder of 0. What's this?
The rest of the problem.
That's the rest of the problem, which would be x squared minus 2x minus 2. That does not factor. I don't think it does. Okay, what do? Quadratic formula, or complete the square. If you like to complete the square, you can do that, or you can use the quadratic formula. So -b plus or minus the square root of b squared minus 4ac. Keep an eye on my arithmetic, please. I got a discriminant of 12. Is that right? Okay. The square root of 12 is 2 root 3, as you know. So this is one of those that we can simplify, right? Remember when you simplify something like this, it's got to be all 3. Now, wait a minute. Weren't supposed to be in this list right here? What list is this? These are the rational roots. Are we guaranteed that every answer is always gonna be rational? Heck no, they're irrational, they're imaginary, there's all kinds of numbers out there. So, yeah, luckily for us, we found one, divided it out, and found the other two using the quadratic formula. Oliver?
Is there ever gonna be a problem where all the zeros are irrational?
Oh, yes, there are. So let's just go on. All right, so here we go. We'll talk about that. at some point. All right, B says do the same thing, only now it's a 4th degree polynomial. Is the fact that it's a 4th degree polynomial gonna change anything about our procedure? No. But what is gonna happen is, assuming we're lucky enough to get one to give us 0, when we divide it out, what are we gonna be left with?
A cubic.
A cubic, which will either factor by grouping, or we'll have to start the guessing process all over again and go through all that again. All right, well, let's see. We got factors of 8 this time over factors of 1. Okay, anybody see one right off the bat? 2? 2 seems like a good option. Let's try it. Okay, unless I messed up, I don't think it's gonna work. I make a lot of mistakes when I do this, so I have to be really careful. I don't think it works, does it? Okay, you wanna try negative 2? I don't know. No, it doesn't work either.
Try 4.
4? Think 4 works? Woo, you got one. I think you got one right there.
That's so bad.
All right, what's left? After we divided out that 4, what's left? X
X cubed.
cubed plus x squared, oh my gosh, minus 2x minus 2?
That's back roots. Can you group it with a 2?
I think I messed up because, again, we can group this one. So let's group it. What do we, take out an x squared and be left with x plus 1. And then a negative 2 and be left with x plus 1. Is that all right? We're gonna kick ourselves because negative 1 was a root. So we were guessing 2s and 4s and all that, and we should have guessed negative 1, but that's okay, we got it. And then what about this? What are the roots that are gonna come out of this?
Plus or minus radical 2.
Exactly. So plus or minus the square root of 2. All right, here we go, number 7. Find the polynomial function, so that's what this is. This is a polynomial function with a leading coefficient of 2 that has zeros at 2, 1/2, and 3/2. It is degree 3. Now, the fact that they added in that little bit of it's degree 3 simply guarantees that none of these are squared factors, right? Because there are 3 factors, and they're gonna give me degree 3. Okay? All right, so what is your thought on this? We're gonna find the cubic polynomial, has these zeros, and leading coefficient, this 2.
Can you put it into intercept form, so like x minus 2, then x minus 1/2, x minus 3/2?
Okay, so one suggestion is that if these are the zeros, then we know somewhere along the line, these are the factors. Now, there are a couple ways you can think about this. When you solve equations by factoring, your factors hardly ever look like this. Didn't your factors, like if you were like starting at the beginning of the problem, wouldn't they look more like this? So we can approach the problem from this standpoint, or we can approach it from this standpoint, whichever you're more comfortable with. We are gonna FOIL this out.
Well, aren't we forgetting 2, like the leading coefficient?
Well, we haven't accounted for that yet. So if we leave our factors like this, if this is what we multiply out, then what will our leading coefficient be? If you just straight up multiply this out, it's going to be 1. So you're gonna have to times it by 2, right? If we use this, which is more typical, that you don't have to do it, if we do this, what would that leading coefficient be? 4, which means we'd have to put a 1/2 out in front. Now, if you FOIL all this out, and you FOIL all this out, they're gonna be the same. It just whichever way's easiest for you to process and think about.
Why would that be 1/2? Because you multiply those things?
Those would give you a 4x cubed if you FOIL this whole thing out, and the problem says the leading coefficient has to be 2, not 4. So I'd have to cut everything in half. Okay, all right. So I'm gonna go ahead and multiply out this bottom one, just so we get a little practice multiplying. And then, so I'm gonna do this one, so I'm not messing with fractions, it's up to you. So if I FOIL those 2 first, it's gonna be 4x squared minus 8x plus 3. And then I'll FOIL minus 16x squared plus 19x minus 6. So I don't know if I'm right, I hope I am. That's what I got when I FOILed my factors. Notice, Sabrina, the leading coefficient is 4. So I'm gonna now, if it has to be 2, remember this is set equal to 0, so it's perfectly legit. If I have to, I'm gonna multiply by 1/2. So my polynomial will be 2x cubed minus 8x squared plus 19 halves x minus 3. We're not used to seeing fractions inside there, there's no rule against it. If I found this laying in the hallway, I'd multiply it all by 2 and get this back again, but it's perfectly okay if you have to have a leading coefficient stipulated. All right, problems, not this one, but the ones we did right before they involve guessing. We talked about ways to narrow down our guesses. Certainly we have the possible rational root rule. We have this stuff about upper bounds and lower bounds. There is another kind of little tool that we have to help us find those zeros when we're out there guessing, and it's called Descartes' rule of signs. Rene Descartes, remember the Cartesian coordinate plane, he's a smart guy. So the Descartes' rule of signs. Did you do this last year?
Yeah.
Good. So we'll just fly through this. Remember, Descartes' rule tells us potentially how many positive real roots we'll have, how many negative real roots we'll have, and how many imaginary roots we'll have. Depending on the problem, this can be a great help, and it can be like hardly any help. Sort of like the PRR rule. If your problem ends in like a 7, the PRR rule is awesome because there aren't many options. But if it ends in like a 96, who cares, right? I mean, you're gonna end up trying everything anyway. This is the same one. All right, so this can be helpful or not. Just try it and see. Who remembers how it works?
The number sign changes.
Exactly. In the original problem, when you're doing positives, you just look at the original problem. Notice positive, I'm talking about the actual signs in the problem. Positive, positive, negative, so there's a change. And then back to positive, so there's another change. So the terms flip-flop back and forth from positive to negative twice. This is what makes Descartes' rule so hard. Because there were two, or not hard to use, not hard to do, but hard to use. Because there were 2 sign changes in the original problem, that tells me that there could be 2 positive real roots. There could also be none. Because of the fact that complex roots, imaginaries, always come in pairs, everything here is counted by 2s. So we got 2 sign changes, we have to decrease that by 2. If there had been 3 sign changes, it would be 3 or 1. If there had been 4, 4, 2, 0, you just count down by 2s, so you can't anymore, okay? Now, how do we do the negatives? Do you remember what we do to do the negatives? Well, pretend that x is a negative number in the problem. Pretend you're putting in a negative number. If x is a negative number, then that term will be negative. This one will still be positive. This one will be positive. And that one, of course, will be positive. So these are the signs of the problem if x is negative. Well, how many times do they change? Once. Now that's helpful, because what does that tell me? There is 1 negative root, period. So if I'm guessing, and I find -3, now wouldn't be part of this problem, but you know, I have another problem, I'm guessing a -3 works, then that tells me don't try any more negatives, because there's only 1 negative. Well, how many roots does this problem have altogether? 3. If 2 of them happen to be positive and 1 is negative, then there will be no imaginaries. But what if none are positive and 1 is negative? Then there have to be 2 imaginaries. This row of numbers has to be even, because imaginary roots come in pairs. Think about every time you've gotten an I. hasn't it been something like this? Every time you do it, you get 3 plus I and 3 minus I. They always come together. So you can't have an odd number down here. Marin?
So when you were putting the, to see the possible negative real roots, when you get to negative x, do you still put in, or like minus x, you still put in negative x?
You put a negative number. I'm not putting in any x's. I'm simply saying if I put in a negative number and cube it,
Okay.
it will be negative. If I put in a negative number and square it, it will be positive. If I put in a negative number and multiply it by negative 1, it will be positive, right?
Yeah.
Yeah, that's what I'm doing. Okay, so let's look at the next one. Do exactly the same thing. X cubed plus x squared plus x plus 1. Alright, how many sign changes do you see? 0. That is good news. That's good news, because I know this is a 1, but let's say that had been a 48. Lots of PRRs don't try any positives, right? Forget those. Now, what about negative reals? All right, if x is a negative number, this term will be negative, this term will be positive, this term will be negative, and that one will be positive.
4, 3, or 1. Oh, yes.
So 1, 2, 3 changes. So 3 or 1. If you have no positives and 3 negatives, and there's only 3 altogether, then there won't be any imaginaries. But if there are no positives and 1 negative, then there will be 2 imaginaries. All right, do C and D on your own so you can figure out C and D.
You have to go first.
Oh, wow. If I did it right, C is like the perfect situation. Huh?
Should you three have to square it, even though it's not in there?
No, because it's not signed. Remember, 0 has no sign, so it can't count for any sign changes or anything, so no. No, you do not need to worry about zeros, guys, they aren't signed. So you can't count sign changes with zeros. So we don't worry about them. The only time we absolutely have to have zeros is when we're doing synthetic division. Wow, these are both awesome situations. Because there's no ambiguity. It is what it is. So, did you get 1 sign change here for the positives?
Yeah.
And then when you put in a negative number, you got no sign changes? So that tells you that there are 2 imaginaries. Don't say 2 or 0. There can't be 0. Because you have to have 3 altogether. And if you have 1 and none, then you gotta have 2. Over here, I got 1 sign change in the original problem. Then when I put in a negative, I still got 1 sign change. Since there are 4 altogether, if I have 1 positive and 1 negative, then there are 2 imaginaries.
So if we get like 1 imaginary, we should assume we did something wrong.
It's not an assumption, you did something wrong. Yep, can't happen. Or 3 or anything like that. All right, let's see if we can get 2 more problems done and then I'll shut up for the day. All right, here we go, biological research. Stephanie does stuff. Find what maximum turkey population is, when it occurs. Okay, all right. So what do you think about this? horrible equation that I don't even really wanna write down, except that's just zeros in it. And it gives us the population of turkeys at time t. What can you tell me about t? It says for appropriate values of t. What can you tell me about t? It's days, so it has to be positive. So x min, or t min in this case, x min, is going to be 0. So I'm not sure how your window is set. What about y min? What about y min? As I'm sitting here setting up my window. Isn't y this? And so y is the population. So 0 for that too? Alright, and then I don't know about the other. Take a wild stab at it and see what
Could you
happens.
say it's at least 100 for the one?
What should our x max be again?
I don't know. Figure it out. I have no idea. I put in my own numbers and let's see what happens when I graph this equation.
I put my one next to that.
Okay, so what? Really? I only have one less.
Oh, well, you should make your x and y.
I put 0 to 90 for my X.
There it
No,
is.
it went up and down. So I just said, oh, I was gonna say.
Okay, finally.
How'd you go through your Y max? Got it.
Yeah.
All right. I am
It was
looking,
actually like, can you add it?
okay. When it says find the maximum turkey population and when it occurs, that kind of clued me in that I ought to be seeing some kind of curve. So in the beginning with my settings, I was just seeing something that kind of went like this. So what did I do? I'm supposed to be finding a maximum. This doesn't have a maximum. So at some point it had to do this, right? So what did I do? I just played around with my X's and Y's until they got big enough for me to see that. Okay. Has anybody found that yet? I did, but they're big. What did you find?
Yes.
600. Oh, I got 340. I mean, 460.
Yeah, I got 300 and 460.
Wait, you got 300 and 460. Yeah.
What'd you get?
I got 4. Oh, wait, so did I.
Yeah.
Yeah.
This thing's gonna be enough for
Okay,
If
so
you want-
you finally
if you ever
saw
wanna
it
turn
come
back
up.
on again.
Okay, and where did it come up? What was it, 300 and
I wish mine could do that.
460? All
You know
right,
what?
so
My friends-
stop.
my friends used to-
Find the maximum find what the maximum turkey population is and when it occurs.
400.
So how many turkeys? 460. How many days? 300. Perfect. Assuming that this model continues to be accurate, when will the turkey population become extinct? Now, I presume you found this maximum because the curve went up and came back down, right? If it just keeps coming down,
Extinct.
won't it at some point have a population of zero? Okay, so find that point. That will be when it is extinct. What you got?
523.
523.
23.
So when, anybody else get that, 523? So, and that's a zero, that's the next intercept. So when does the turkey population become extinct? After 523 days. 1 minute. Sunspot Small Appliance Company supply function for their Evercurl hairdryer. Okay, so the supply function is 6 plus 0.001 P cubed. And the demand function, sounds like an econ problem, is 80 minus 0.02 P squared. And P is the price, so that's supply, demand, P is price. Determine the price for which the supply equals the demand and the number of hair dryers corresponding to this equilibrium price. So, seniors, who's in econ? Have you talked about equilibrium?
Yes.
That's where supply and demand, that's like the perfect situation. You have exactly how many you need. Supply and demand are crossing. So, to find that, won't we just set these equal to each other? If you want, you can then just enter them both as separate equations and look for where they intersect. You could also move everything over to one side and graph it like you did this one, whatever's easiest for you. Yeah, my window's all messed up for the last one. Are they intersecting for you?
Yeah.
What's your,
0 to 500.
We're looking for where they intersect. So my point of intersection, 36.27, comma, 53.70.
Yeah.
Is that what you got?
Mm-hmm.
Okay, so now we need to interpret that. Remember, our variable was the price, so what does this tell me right here? I should be charging $36.27 for my hair dryers? And what is this now? That's your Y value. So isn't that your supply and your demand? That is the number of hair dryers you need to make. So obviously you can't make 0.7, so about 54 hair dryers is what you need to make to achieve that equilibrium price.
What's X value?
Says that's the price. Tell me that in the problem, that's the price I'm gonna charge. All right, perfect. 2.4 will be due on Thursday. Some point we're gonna have a quiz too, because we learned a lot of things.
This week?
I don't